The examples in this video go with lesson 11.2, the least squares regression line. Example 1. The following table presents the percentage of students who tested proficient in reading and the percentage of students who tested proficient in math for each of the 10 most populous states in the United States. Compute the least squares regression line for predicting math proficiency from reading proficiency. Okay, now, here's the table, and you may recognize this because we already found the mean for the x's and the mean for the y's and the standard deviations and everything in lesson 11.1. So what I'm going to do is I'm going to go back and I'm going to pull up that information that we have already calculated. Okay, so you can see I pulled up the information that we had last time. Here's the mean, 71.8 for the x's. Here's the standard deviation we found, and I rounded it off to 4 decimal places. And the mean for the y's and the standard deviation for the y's, again, rounded off to 4 decimal places. And then the correlation coefficient that we calculated. All right, now to find the equation for the regression line, we're going to use the formulas back here. All right, here's the equation. You might recognize this as y equals mx plus b, where this is the b, b1 is your m, and of course, we've got our y back here. Okay, we want to find b1 first, and the way we do that is to multiply the correlation coefficient by the standard deviation for the y's divided by the standard deviation for the x's. All right, so this is going to be our slope. We're supposed to take our correlation coefficient and multiply this by the standard deviation for the y's divided by the standard deviation for the x's. All right, and let's put this in the calculator and see what we get. This is going to give us 0.8230 if we round this out to 4 decimal places. Okay, now we're going to figure out what our y-intercept is. That's our b0. And we're supposed to take the y-average minus the slope we just found times the x-average. All right, so to find our y-intercept, we're going to take the average of the y's minus the slope we just found times the average of the x's. All right, and let's put this in the calculator and see what we get. And rounding to 4 decimal places, it's giving me 11.0086. So the equation for our least squares regression line is y is equal to our y-intercept plus our slope times x. Now, if you want to switch those around and write that as 0.8230x plus 11.8006, that's perfectly fine, because that's the way that we're used to seeing these equations written, because we're all used to y equals mx plus b, and I have no idea why your book is doing it backwards, but there you have it. Also, I'm going to post a video that shows you how to use your calculator to find the least squares regression line so that you don't have to do all this stuff by hand all the time. So your calculator, this is the one that was actually recommended for this class, okay, will give you the correlation coefficient, and it will also give you the coefficients, like right here, your y-intercept and your slope, so that you can find the equation for the regression line. Example 2. At the final exam in a statistics class, the professor asks each student to indicate how many hours he or she studied for the exam. After grading the exam, the professor computes the least squares regression line for predicting the final exam score from the number of hours studied. The equation of the line is y hat is equal to 50 plus 5x. Part A. Antoine studied for 6 hours. What do you predict his exam score to be? Well, since x stands for the number of hours studied, and our y hat is going to represent the score on the exam, we are going to use our model here, and we are going to substitute 6 for that x. So we have 50 plus 5 times 6. And if we put that into our handy dandy calculator, that will give us 80. Now, this does not mean that Antoine actually got an 80 on his exam. This is just based on the amount of time that he studied, what we would expect him to get. He could have got an 80, he could have got more than 80, or he could have actually got less than an 80. But our model says we should expect him to get an 80. All right, part B. Emma studied 3 hours longer than Jeremy did. How much higher do you predict Emma's score to be? Now, we can do this a couple of different ways. We can put in, we can pick any number we want to for Jeremy's study time. So we can say maybe Jeremy only studied for 1 hour, and then that means Emma studied for 4 hours because she studied 3 hours longer than he did. And then we can put both of those into our model right here, and then we can subtract the scores, and we'll know how much higher we predict the scores to be. Or there is a shortcut for figuring it out, and right here, if the values of the exploratory variable differ by an amount other than d, their predicted values will differ by a times d. So this is actually saying we should be multiplying the slope times d, whatever that difference is in the amount. In this case, the difference between the amount that Emma studied and the amount Jeremy studied was 3. So in this case, our difference would be 3. And then the slope that we have, that's right here. That's 5. Therefore, we would predict the difference in their scores to be 3 times 5, or 15 points. So we would expect a 15-point differential between Emma's score and Jeremy's score. Now, again, that doesn't mean that there will be exactly 15 points. There could be more, there could be less. We don't really know, but our model says this is what we can expect to happen. If we do it the other way, and let's say Jeremy did study for 1 hour, all right? So if Jeremy did study for 1 hour, his predicted score would be 50 plus 5 times 1, which will give us 55. And then Emma, who studied 3 hours longer than that, or 4 hours, her predicted score is 50 plus 5 times 4, which is 70. And so the difference in their scores, 70 minus 55, which will give us 15 points. So either way, we could have done this, and we got to the same conclusion. We're expecting there to be about a 15-point differential between the two scores. Example 3, for each of the following plots, interpret the y-intercept of the least squares regression line if possible. If not possible, explain why not. Part A, the least squares regression line is y hat is equal to 1.98 plus 0.039x, where x is the temperature in a freezer in degrees Fahrenheit, and y is the time it takes to freeze a certain amount of water into ice. Well, the first thing you should recognize about this graph is it's a little bit misleading because the y-intercept happens when x is equal to 0, and that is not going to be back here in the corner. This is not my y-intercept right here. In fact, x is equal to 0 at this point right here. And so our y-intercept would be in this area. And we know that y-intercept is 1.98 because of the model for the equation that we had right there for the regression line. Okay, so we know that when x is equal to 0, y is equal to 1.98. This is our y-intercept. Okay, now, what does that mean? Well, remember, y stands for the time it takes to freeze a certain amount of water in ice. So it's going to take 1.98 hours. And then x stands for the temperature in a freezer in degrees Fahrenheit. So we've got 0 degrees here. All right, that means it will take 1.98 hours to freeze a certain amount of water into ice in a freezer whose temperature is 0 degrees Fahrenheit. All right, so here is our interpretation for our y-intercept. It will take 1.98 hours to freeze a certain amount of water into ice in a freezer whose temperature is 0 degrees Fahrenheit. So here's my y-intercept, and here is x. Still on example 3, this is part B. The least squares regression line is y hat is equal to negative 13.586 plus 4.340x, where x represents the age of an elementary school student and y represents the score on a standardized test. All right, let's back up a few slides to this comment right here. If the x values are all positive or all negative, then the y-intercept does not have a useful interpretation. If we take a look down here at the x-axis, our lowest value is 4. And we look at our data, and we don't have any data that goes past 4. Okay? That kind of makes sense because if this represents the age of an elementary school student, first of all, we're not going to have any 1-year-olds in first grade or in elementary school. We're probably not going to have any 2-year-olds. There may be a few documented cases of 3-year-olds, and we still allow people to start kindergarten at 4, but they have to be an older 4. And of course, we can't have an age in negative numbers. So the fact that all of my x values are positives tells me that our y-intercept doesn't really have a useful interpretation. And that's the reason, because all of my x values are positive. Okay, so let's write that down. All right, and so our conclusion right here, the y-intercept does not have a useful interpretation because all of our x values are positive. Example 4, the Sanchez family wants to sell their house, which is 2,800 square feet in size. Mr. Sanchez notices that the slope of the least squares regression line for predicting price from size is 0.0992. He says that if they put a 250 square foot addition on their house, the selling price will increase by 0.0992 times 250, or $24.8 thousand, which is the same thing as $24,800. Is this necessarily a good prediction? And we're supposed to explain this. Okay, notice what he's doing right here. He's taken the slope and he's multiplying it by the difference to get that 24.8. Okay, now let's back up to this point we had right here. If the values of the exploratory variable differ by an amount d, then their predicted values will differ by a times d, or we said this would be the slope times that difference there. Okay, we've got the values of exploratory variables. So we're looking at comparing two different values. Now, what Mr. Sanchez didn't take into account was he's comparing his house to his house. And what this slope is actually telling us is if we have two houses that differ by 250 square feet, then we can multiply it by that slope and we can see there's probably a $24.8 thousand differential. But he can't make this claim based on comparing his house to his own house. All right, and here is our explanation right here. Okay, so no, this is not a good prediction because the slope tells us that two houses that differ in size by 250 square feet would have a price differential of $24,800.